So, our next presentation, it's going to be delayed for a few more minutes. Thank you, Jonathan. So our next presentation is on Titan's gravity field and interior structure after Cassini by Daniele Durante.
Hi. Yeah, I know the break is too short, unfortunately. Okay, so I'm Daniele Durante from Sapienza University of Rome, and today I'm going to talk about the result from Cassini for the gravity field of Titan and some basic implication for its interior structure. So Cassini completed 126 flybys of Titan, 9 of which were dedicated to the determination of the gravity field of the moon, with the aim of inferring its interior structure. During these passes, the high-gain antenna of Cassini was pointed toward the Earth in order to collect radiometric data, which were then used to determine the trajectory of Cassini and thus the gravity field of the moon. So the first analysis of the gravity data were collected indeed when Cassini was still collecting data. So yes, in 2010 provided the first determination of the gravity field of Titan up to degree and order 3. Whereas in 2012, the first determination of the tidal response to eccentricity tides forced by Saturn was presented. More recently, in 2019, I published an update on Titan's gravity field, which was based on the analysis of all the 9 gravity passes, plus the addition of T110, which was a high altitude pass in which gravity data were collected with the low-gain antenna instead. So the radio science experiments can exploit either the deep space transponder or the Ka band translator. The first was able to provide either S, X, and Ka band links with the Earth, whereas the Ka band translator, as the name suggests, could have provided a very accurate Ka band uplink, Ka band downlink link. But unfortunately, the KAT failed before Cassini arrived in the Saturnian system, so we could only exploit XX and XKA data. So the gravity investigation exploits indeed the radio signals transmitted from ground to the spacecraft and then retransmitted back to the ground station in order to measure the Doppler shift of that radio signal and thus determine the radial velocity between the ground station and the spacecraft and thus reconstruct the trajectory and the gravity field of the moon. So here you can see the ground tracks of Cassini. You can see that all the different trajectories had different orbital geometries, but however, the sampling over the surface of Titan is not uniform, with the equatorial region being sampled more than the polar regions. So this reflects also in the results for the gravity field, in which we can indeed expect better accuracy in the equatorial region, whereas in the polar regions, there will be a higher uncertainty in the gravity anomalies. So looking at the altitude of the closest approach, the maximum was reached in Titan Pass T75-4 with an altitude of 3,600 kilometers, whereas the minimum was achieved during T22, where the altitude was only 1,300 kilometers, where the effect of the atmospheric drag became important. and thus it must be accounted for when we integrate the spacecraft trajectory. So indeed, the data analysis was performed with JPL latest orbit determination software, which is Monty, and we accounted for all the effect, able to produce an acceleration large enough to perturb the spacecraft motion to a level that can be probed by the radio science instrumentation. Concerning the estimated parameters, we indeed estimated the gravity field coefficients in terms of spherical harmonics up to degree and order 5, and we will see later why we selected degree 5. In addition to that, we also estimated the love number, which is which describes the tidal response of Titan to the eccentricity tides forced by Saturn. And we also had to include, as I anticipated, the modeling of the drag acceleration, which is especially important in low altitude flybys. And we accounted also for the effect induced by the anisotropic thermal emission from the onboard radiothermal generator, which even if it's small, it's sufficiently large to be, that must be accounted for. One key element for the analysis is in the way we accounted for Titan's orbit, because indeed the positioning of Cassini with respect to Titan was very accurate to the level of meters or tens of meters in the radial direction. And thus also the positioning of Titan with respect to Saturn must be accurate as well. So in order to prevent biases in the estimation, we decided to update the Titan ephemeris in each arc, which again allow us to prevent biases in the estimation at a cost of a small increase in the uncertainty, which is in the order of 20%. So here you can see instead the Doppler residual that we obtained after the fitting procedure for all the passes, which is compatible with our expectation for from a noise model for Cassini. The RMS value of the Doppler shift ranges from 17 to 66 micron per second at 60 seconds. According to the data arc, and we preferred two-way data over three-way data when available, given the higher stability provided by a two-way coherent link, indeed. And we preferred X uplink KA downlink data over the standard navigation XX passes, given the fact that the KA band in downlink can decrease the effect induced by charged particles. So this configuration allows us to calibrate for plasma particles in the downlink leg, thus improving the data quality. In addition, for the data calibration, we exploited the advanced media calibration system, which uses the data from the advanced water vapor radiometer on the Earth to calibrate for the effect induced on the Doppler shift of the radio signal from the Earth troposphere, thus improving a lot the data quality and again preventing biases in the estimation. And in our results, this particular calibration of the Earth troposphere can shift the estimate by about twice the formal uncertainty. So it's something very important to consider. So going to the results for the gravity field coefficients, here you can see the numbers of all the coefficients. With in red, the coefficients was estimated value is larger than 3 times the formal uncertainty. So the coefficients which are very well determined. And you can see that apart from the degree 2 coefficients, also the sectorial harmonics of degree 3 and 4 are very well determined, and this is a result, of course, of the very good and broad coverage in longitude that we have from Cassini passes. Also, you can notice that none of the degree 5 coefficients has been determined to that level of accuracy, but still the inclusion of degree 5 is important on a local scale, but it's not supported on a global scale on Titan. This can be seen also in terms of a degree strength map, which is a map in which each point represents the maximum degree whose expected acceleration is larger than the corresponding uncertainty on that point. So you can see that indeed the dark green regions corresponding to degree 3 is the regions where we essentially have no coverage from Cassini, so the resolution is indeed lower. Whereas where we have more flybys, essentially the anti-Saturnian point, close to the anti-Saturnian point, here we can have a larger resolution and we can reach degree 5. So this means, as I said, that degree 5 coefficients, so that resolution is achievable only in that particular region of the moon, but not supported on the whole moon. From this map, you can also see that instead the degree 6 coefficients are not observable with Cassini data, and that's the reason why we stopped our analysis just to degree 5. So here in the plot, I reported the root mean square of the gravity coefficients as a function of the degree, so the power spectra. And you can see that the estimated value for all the different degrees, so the red line, is larger than the formal uncertainty, which is instead the dashed black line. I also reported as a comparison a fit of a Cauchy rule, which is an empirical power law of the type a constant divided by the degree to the power of 2, which fits reasonably well the degree larger than 2. I will comment that in a moment. Let's look at degree 2, which instead is dominated by the aerostatic equilibrium, which is what we expect for a body like Titan in synchronous rotation with Saturn. So the Cauchy rule, as I said, is an empirical power law which describes pretty well the power spectra of terrestrial planet. It has been observed on the Earth, on the Moon, on Mars, Venus, etc. And as I said, it's just a coefficient divided by the degree to the power of 2. So the coefficient is pretty interesting because it's affected by the degree of compensation that we may have in the gravity field, the volume of the region responsible for the gravity anomalies, and the typical stress level that we have in the body. So for terrestrial planet, we know that the Cauchy rule scales, the coefficient scales with the surface gravity to the power of -2. But if we were to apply the same rescaling to Titan, we would overestimate the field by a factor of 50. However, this is not surprising since on Titan we have a large degree of compensation, and also the strength of ice is smaller than the one that we might have on a rocky planet. Unfortunately, Titan is the only icy satellite whose gravity field has been resolved to degree 5, so we cannot make a comparison within this class of bodies at the moment. But in the future, JUICE and CLIPPER can provide new hints on the topic with the moons of Jupiter. Oops. Going to the tides, so you can see that the different flybys had a pretty good coverage in mean anomaly of Titan along Saturn. So we were able to determine very accurately the effect time variable component of the quadrupole field on Titan, and our best estimate of the log number is 0.62 plus minus 0.07. So confirming the large deformability of Titan on the time scale of its orbital period. Concerning the time lag, if we include in the estimation the time lag, the angular lag, we obtain a value of 4 degrees, which is pretty large, but however, the 1 sigma uncertainty is larger than that value. Thus, we can draw no strong conclusion on the internal dissipation on Titan. So moving on, the implication for some basic implication for Titan's interior. If we look at degree 2, as I said, it's compatible with the hydrostatic expectation with a moment of inertia in the vicinity of 0.345. Whereas we know that Titan topography instead departs substantially from the hydrostatic expectation with the geoid, which is the small purple ellipse on the right, is instead very far from the topography. So if we assume a pretty simple structure with a central rocky core surrounded by a water layer, which includes different phases of water at different pressure and temperature, so just an average layer, and we assume a moment of inertia of 0.345 and a density for the water of 1,000 kilogram per cubic meter, we obtain a shell thickness of 400 kilometers. But however, if we would account also for log numbers, we would obtain a wider range of models. So non-hydrostatic field complicates the picture because we don't see correspondence between gravity and topography, and this is also reported here in the correlation diagram, in which we saw no correlation among at different degrees among the gravity anomalies and the topography, which is an indication of the fact that the gravity anomalies are likely associated to internal heterogeneities. So I will leave here the conclusion, and thank you for the attention.
Thank you, Daniele. Any questions?
So my understanding is the Cowler rule is not really physics-based, but it's empirically based. Is that a fair comment? I mean, it has been criticized on a number of grounds. And so is it really fair to try to interpret the departure of Titan from the Cowler rule in terms of its physical properties? And that may be giving more credence to the rule than it deserves.
I fully agree with that. Actually, you can explain the Cowler rule with random distribution on the surface of concentrated mass anomalies, but still it depends on how the field behaves. So on the Earth, what has been observed is that the Cowler rule fits pretty well the higher degrees, whereas the lower degrees are more compensated, and there is no correlation with that. So actually, it's pretty surprising that here we can fit the lower degrees with a Cowler rule, because it's something that we would not expect. But however, that's just at the moment, it's the only observation, so it's something that is interesting to be investigated in the future.
Thank Daniele one more time. Another question? Thank you, Daniele. We'll move on to the CAPS instrument, the scientific accomplishments and reminiscences from Andrew Coates.